Hey guys, this is Seetharam Venkatesh. I work as part of the greater Hadoop team at Yahoo in Bangalore. I'm going to talk about data management on Hadoop at Yahoo. Let's see what we mean by data management and cover why is it critical for us at Yahoo, and look at what the challenges are in this space, and look at how we have solved this problem, and let's look at what we're looking into the future. What do we mean by data management, right? I mean, it's basically a suite of services for essentially doing two things. One is data motion, which is moving data or acquiring data into Hadoop clusters from various external sources. And since Hadoop clusters are partitioned by access, so we have staging, research, and production clusters, there is a need for us to replicate this data after acquiring across these clusters. And once people have used or processed this data, they want to get these aggregates and export this data to data marts, reporting systems, serving systems, and hence we need to have a service which exports data. So once you have this data within a Hadoop cluster, then how do you manage the lifecycle of this data, right? We can't rely on users to basically manage the lifecycle. So if somebody gets data, they just live it forever. So we want to make sure we retain the data after some time. And again, we can't rely on users to adhere to data governance policies, right? So there is personally identifiable information. We need to anonymize these PII information in our data and have different retention policies for raw data sets and anonymized data sets. And we also have regulatory compliance, which is SAC and SOX, and how do we archive this data from Hadoop clusters to either a tape or some other system, since we need to keep the data around for 7 years. So why is this critical for us, right? So initially, when Hadoop was in its nascent stage, a lot of researchers used to come to Hadoop, and data used to be the carrot for users. So we built a system where you could get quickly some feeds so that they can do some processing, analyze trends, and as Hadoop took off and became a basic batch processing system throughout Yahoo, a lot of users started to come in and asking for SLA guarantees, data quality guarantees, right? And the most important productivity gain here is, we let users focus on utilizing the data than how to get it, how to manage the life cycle of it. So since, the data is huge, right? We've been saying, everybody talks about petabytes of data. We want to optimize the resources, right? You don't want to create a denial of service attack or, bring down different systems within Yahoo. So how do we optimize these resources so that you are polite on these and there are other users apart from Hadoop itself? The other one, as I spoke, is again, we cannot rely on users for adhering to data governance policy. So how do we implement this in this system so that everybody could use these and also adhere to these regulatory policies? So let's look at the challenging data landscape here. So we have about 25 clusters within Yahoo across 4 data centers, and each one running in different versions. So everybody knows about variant compatibility. You can't talk to one using the same client tool. You can't talk to multiple clusters, right? And since we have a rollout which takes typically over a quarter to 2, we will always have different versions of Hadoop. And dealing with multiple data sources which could have different interfaces. Some data sources could have HTTP. Some data sources could have SSH, SCP kind of a thing, FTP drop boxes, NNTP, right? There are different use and flavors of these protocols. And also the API contracts, even if you have 2 data sources on HTTP, the API contracts could be very different, right? They could have different authentication methods. They could, have different isolations. Some such systems can come and, go down, scheduled, unscheduled, right? And you also want to make sure, you work well with, well-performing and slow data sources, right? You can have a mix of these, right? And in data itself, some people want, batch data. Some people want streaming data. You have, mutable, immutable tables. There are different, again, variations there. Some are structured, unstructured, right? So how do we basically work with all these different challenges and build a solution which could, cater to, 80% of the use case, right? Apart from this, there is steady growth in data volumes per day, right? And there are SLA requirements from, minutes to day. There are some in seconds as well, which we don't cater to. And also, when you want to acquire the data, some people have BCP requirements, right? I want to get data to a production cluster, but at the same time, I need this copy on a different BCP cluster. Or some have these hot-warm requirements where, you want to first import and then want to replicate and make sure, they are there on both the places. So other one is, feeds with varying periodicity, right? So you have, every 5 minutes there could be feeds available which we need to ingest and have SLA guarantees. And there are some, varying from daily, hourly, to weekly, to monthly data sets. So let's look at, what we have solved within Yahoo. So, how do we handle these large data volumes, right? I mean, we have seen from few MBs to terabytes of data in each instance, right? So we have front page, and on the hour we have about 1.5 terabytes. We have different properties where, on a daily basis or hourly basis, we have, up to 500 GB to a terabyte on the hour. So how do we handle these huge volumes and still meet SLAs? So we eat our own dog food, right? Since we are part of the Hadoop team, so we basically delegate all the heavy lifting to a map job. So typically, the pull happens as a map-only job as part of the solution. So how do we handle diverse interfaces and API contracts? So we provide pluggable interfaces and adapters, so the acquisition service is very light. So there are 3 architectural choices, that we explored. You could run these adapters as part of your map jobs, right? So when you actually launch a task, you actually invoke an adapter that can actually talk to the source and pull the data. But there were several issues with this, right? So since the task or the pull can run on any compute node, we had ACL restrictions. You cannot open ACLs to all your compute nodes, right, to go and talk to an external system and pull the data. It could potentially be in a different colo as well. So what we did is we actually created a bank of proxies, right, which could have ACLs, open. And if you have different authentication schemes, if you have, let's say, client-side certificates, you don't have to distribute these and manage these as part of your map jobs. So we could essentially have this layer, outside of this and move that there. The other option we also have is the client hosts an adapter, and we have something called HIO, right? Hadoop input output. It's an REST API, and you write the adapters and host that right in front of your source, and you are responsible for actually implementing the source adapter. So these are 3 modes that we have, and we support the latter 2. So each data source have different capacity to serve. So what I mean by that is, some data sources could have, can actually have 5 or 10 servers in front of it and can serve, 500 Mbps per second, or some data sources could be very, very slow because there are other consumers as well. So how do we handle this, right? So we basically have a queue per data source. So, we also, if you take, even a Hadoop cluster, typically, you can have, slow and, slow performing job trackers or data nodes. Some job trackers keep going, running into out-of-memory exceptions. So we have to work around that and make sure whichever is well-performing is not affected by a slow-performing data source, right? And we also have implemented resource management. So you can specify, and the specific resource that I'm talking about is bandwidth, right? You can specify bandwidth between 2 data sources. So if you're doing acquisition or even replication, you can specify, I can have 100 Mbps between these 2 sources. So across data sets that we are pulling, we manage this bandwidth and be polite on the data source. So data source isolation, right? So you could have maintenance windows. So again, scheduled or unscheduled, you still want to work around these maintenance windows and make sure we are making progress. So we have implemented asynchronous scheduling, and progress is monitored per source here. So varying data formats. So we have, people have, custom data formats. You have field delimiters as control A and, record delimiters as control B. Some have text with new line characters. Some have binary. So we enable our users to actually take that and convert to a sequence file or, RC file, which is more efficient and suited for, processing on Hadoop. So we do that as a MapReduce job today. And we've seen the file sizes are varying, right? I mean, some people have, 400,000 1 KB files, right? Or, having 40 to 60 GB files, right? Many of them within a data set. So what happens on HDFS is, if you have a very small file, you're just eating up into namespace. So what we have done is, we've implemented coalescing of these small files into a file which is equivalent to a chunk size in HDFS, right? So we coalesce the small files into 128 MB, which is what our chunk size is at Yahoo. And most of the large files are already compressed, right? They are gzip files. And since we know that MapReduce jobs, these star files or gzip files are not splittable, we split these large files into smaller chunks of 128 MB so that you get an even spread. See, essentially you're getting this so that you want to actually use this data by running through a MapReduce program. So we split this so that you get an even spread, you get better locality, right? And you don't have to worry about long tails at all. So we reduce a lot of long tails in the processing afterwards as well. And the most important thing here is we have built-in failures. And when we are pulling a file, if it fails, right, either because of a checksum validation or you've dropped a connection, so we retry and we implement checkpointing. So it retries if a map job itself fails, we retry the job and we start from where we left off without downloading all the files. So data quality is an important thing that we've built in. So people want checksum validations. We support 3 things today. So file sizes, row counts, and checksums. So we have, post acquisition or replication, we run through a verification job, which is again a map-only job. And if people have configured different things, we actually check, how many rows have we acquired? Does it match what the source published? And it's completely pluggable. And as I spoke, we support BCP. So we support different configurations here. So if you have, at the source itself, you have a BCP, we do a parallel pull to our Hadoop clusters, which is the production to production and BCP to BCP. If you don't have a BCP at the source, we do a parallel pull from the same source. Let's look at replication. Again, as I said, we have clusters partitioned based on access. So we have a lot of clusters, and data is replicated up to 15 clusters in certain instances, which is pretty bad. But there are limitations in Hadoop itself, right? You can't scale beyond 4,000 nodes because job tracker croaks. Of course, with the .next, we should be able to actually enlarge and have a larger cluster. So again, like acquisition, all the replication is happening through a map-only job. So this is the most critical thing that we have solved. So since you can have a large number of clusters across colos participating in a copy, you need to make sure you're not actually using the cross-colo bandwidth, right? Which is very, very important. So what we have done here is, we actually create a tree of copies, and with at most 1 copy across the colo. So it's a tree of copies. So first level of copy is a fork within the cluster and 1 across the cluster, across the data center. And the second level of copies is within those data centers. And you can have up to 3 or 4 data centers participating in these copies. And all this is managed by this service without any user intervention, right? So if you can see the colored ones here are, are the ones which is in the second level. So we also have worked on the next gen. I don't know how many of you know DistCP here. Distributed copy is a tool that is part of Hadoop MapReduce core, which is used to copy data between 2 clusters. It uses HFTP to actually pull the data and uses HDFS to write it to a local cluster. So there were a lot of issues in DistCP in its current form. One is it's like 4,000 lines long. Second, most of the calculations of the splits, and it's more like a glorified rsync. So it does a lot of computation on the client side before launching the MapReduce job, right? So what we've done is there is a lot of setup costs. So we've reduced this and do this as part of the map job itself, right? And the other thing is, so typically the splits are very static, right, in MapReduce. So you have n number of files that you want to copy. You actually split that into n number of how many of your tasks you want to launch based on how many resources are available. Let's say you have 10 tasks and 100 files. You actually split them into 10 buckets, each having 10 files, right? So let's say, and these files can have different sizes. So the task that is actually working on a bucket, could potentially hit a slow data node and can become very slow. So it doesn't make any progress. But let's say other map tasks are making a lot of progress, and you have a long tail here. So what we've done is, we've created a dynamic input format where you don't do this assignments ahead of time, right? It's not static. So we essentially created a queue on HDFS, and each task actually picks up a file to work with, and if it's slow, it's just that file. The other, mappers or which are faster can pick up other files and make progress independent of a slow task. And this is going to be open source soon. So data export is essentially, if we support both models, push and pull. So in push, we've implemented as a target and replication. So data gets pushed, and it's copied to an external system. But we also have another tool called HDFS proxy. So this is an HTTP RESTful API over HDFS, and it provides a full file system API, so you could do full read and write. And we use, this is what users use to pull data from HDFS using, HTTP. The other thing that gives, that this is very useful for is, you can work across multiple versions, right? You could use standard Unix tools like, curl, wget to work with HDFS without needing this client-side jar. So let's look at lifecycle management. Again, once the data is on the cluster, right, what do we do with the data, right? Somebody has to manage this lifecycle. And we typically know data becomes cold pretty soon, right? And once there's access frequency we've seen, it drops like 50% after the first few weeks, and drops to less than 80% after 12 or so weeks. So why do we need to have this on Hadoop, right? Since Hadoop keeps, HDFS design is to basically for reliability and availability, right? We have 3 replicas of data. So how can we actually, make sure we are not using up unnecessary space which is not used? So we've implemented detention to remove old data. So we also handle data privacy. So there are a set of rules that are governing, for each personally identifiable information like, IP address, user ID, some people even, have social security numbers that they search on. So we want to remove even the query terms, basically, right? So how do we anonymize these? And there are a set of rules that is defined by this data governance policy within Yahoo. And we have implemented these rules so that users don't have to worry about it. So we always, whenever it needs to be, PII compliant, we create 2 feeds, right? One is the raw feed, which has very less retention, based on, again, policies, and the other data set is the anonymized data set, which can live longer, right? So, and we handle, these policies differently. So other thing we've done is SOX compliance. Typically, you have to have the data for 13 months if it needs to be SOX compliant. There are ways that we are exploring, in HDFS. So most of the data typically is used for a couple of weeks to, few tens of weeks. And keeping this data around for 13 months just doesn't make sense, right? So we initially evaluated, can we reduce the replication factor? Can we offload this to an intermediate store like NAS or a nearline store? So there are bugs in HDFS where if you reduce replication factor to 2, you don't have guarantees that you have the replica in one rack and another rack. It could end up in the same rack, which is fixed in 23. But then the cost is very high, right? I mean, HDFS is probably 3 or 4 times the cost compared to a tape, and probably twice as expensive compared to a NAS solution. So we decided that we will shove it into a tape, and we have built archival and restoration to and from tape for both SOX and SEC compliant. So users need not worry about this, right? I mean, user comes and says this data that we are acquiring needs to be SOX compliant. So we automatically manage that, put it in a tape, and give them, if they need to reprocess, we will give them a way to restore the data and reprocess. So most important thing is operability and manageability, right? Since we are, onboarding, thousands of feeds and, terabytes of data, we need to be operable. So we provide a central dashboard for monitoring and administration, an integrated view of jobs running across clusters and colos, SLA management, plus we collect a bunch of metrics with ETAs and SLA misses based on the history of these data movement. And the cool thing that we have done, which is not there in any component in the stack, is one instance across clusters within a colo. Like if you look at Uzi, if you look at HCAD, it's one instance per cluster, and this is one data loading instance per colo. And how have we solved this? Interoperability across Hadoop clusters in a colo. We have written a reverse class loader, so we're using some class loader tricks to work with multiple Hadoop jars. And since it's a very simple command pattern, we will load these along with the Hadoop jars that we are working with that particular source. So we do handle maintenance windows and failures and system shutdown when a daemon is shut down. We automatically resume upon restart all the data loading jobs, and we also support partial copy and auto resume. So let's briefly look at the architecture here. As I said, we have 3 daemons for acquisition, replication, retention. So we have introduced an abstraction, a workflow abstraction on top of these MapReduce jobs. So each acquisition or a replication or a retention is essentially a workflow with a bunch of MapReduce jobs. Those are launched against a Hadoop cluster. And as I said, we have a bank of proxies, and it's HTTP between a Hadoop cluster and this proxy, and eventually it can farm out an SCP or a FTP or a HTTP request to these data sources. And data movement, is the other way. So we also have a central dashboard with, a nice configuration service, and we provide a UI for operations or users to configure these. And all the transitions and the status of these feeds are stored in a runtime database. The highlights. So I said, we've introduced workflows as an abstraction. There are more workflows, these data movement workflows than Uzi workflow within Yahoo. Amounts to about 30% of the jobs launched on our clusters. But since we do resource management, we have very less number of map tasks, which result in less than 10% utilization of our clusters. It solves recurring batch data transfers. We have about 2,300 plus feeds with varying periodicity. So 5 minutes to monthly, and 100 plus terabytes per day of data movement. Again, manageability, we have SLA monitoring and with EDA, and works across incompatible Hadoop versions. So future, we're looking at Edge catalog. I think there was a talk on Edge catalog, Hadoop tables, and Uzi. We have written our own workflow because we kind of were born together, and we plan to integrate Uzi for the workflow part. So we are also looking at self-service. Today it's a managed service within Yahoo, but for users, ad hoc users, and users who don't have a lot of requirement on resource management and stuff, we want to enable self-service. Support for event-level data through HDFS proxy, and storage efficiency. As I said, right, access frequency drops, and we want to make sure we don't want to have 3 replicas when you don't have many jobs running. So how do we actually reduce the storage requirements for HDFS? So thanks for listening.
I came in late, so sorry if you already covered this, but I was curious, what is the name of the system, and whether this is going to be open sourced or not? What's the status from that point of view?
That's a good question. So the name of the system, internally we call it GDM. So we've built two generations of data management system at Yahoo. The first incarnation was just acquisition. We used to call it DAC, data acquisition. And then, it was so simple that, we could reuse a lot of things and started doing all the policy management and, lifecycle and other cool stuff. So it's called GDM internally, Grid Data Management. And we had plans of open sourcing this, but, we are working on a next 3rd generation application, which is basically using Uzi, Edge catalog, and making it a set of APIs, client-side libraries, so that you can do a lot of customization with, the code that we have, which is running in production. So that is what we plan to open source. So the adapters that we have is completely specific to Yahoo, but even though it's open. So I don't know how much sense it makes to actually open source the existing one. So we plan to open source the new one. And we are planning to open source all the tools that we use, like DiskCPV to HDFS proxy, pretty soon. Thank you.
Do you do any data center, cross data center replica management, or you go with a simple policy of 3 replicas per data center? And follow-up question is, I think Facebook has done some good work on high tide.
Yes.
Are you looking at that as part of your answer to my question?
Great question. Yes, we are. So since we about 18 to 20 petabytes of data is duplicate data across clusters, we are actually looking at high tide. The only issue is basically security, right? All our clusters are secure clusters against Facebook's, which is not. So I'm working with Dhruba actually, so to see how we can reuse high tide here. We definitely are using rating that they have done, but it's a different solution. But we are using the rating part in HDFS that they have done, and we are already in the process of rolling that out within Yahoo. Yes, we reuse. Thank you.
You mentioned about data quality and how you plug in data quality modules. 2 questions there. One is, what kind of modules are these? Are these vendor build module, internal modules? And the second part of that is that data quality aspect map reduced as well when it runs?
Good question. So, they are not vendor modules. It's what we have rolled out based on the requirements that we have within Yahoo. So let's take a classic case, right? HDFS has a weird way of calculating checksums, right? It calculates checksums for every 512 bytes, and then there's an MD5 of all these checksums, right? So when you export data, right, how do you actually verify that you export right data? So we are providing a tool for users as a client-side library to actually verify the checksum when you export the data, right? Okay. Now when you import the data, we out of the box support checksums, right, straight checksums, and row counts, and file sizes. So if you have anything else, you have to work with us and to build a pluggable validation. We have a pluggable validation framework, right? So we need to build that, and it's very, very generic when we actually, there are 2 steps in acquisition, right? One is a discovery API, and the other one is a download API, right? So when you actually discover, right, the metadata publishes that what kind of statistics do you have on this data, right? Today we support only 3, but it's completely pluggable. And this is a map. Yes, it is. It runs as a map reduce job, a map only job, the verification.
You talk about masking and redaction. When does that happen? Does that happen before the data gets loaded into the cluster, or after you've extracted data, then you're masking it?
You mean the coalescing and chunking?
No, I'm talking about different. You talked about data masking, right? Data privacy or some aspect.
Oh,
of
okay.
that.
Okay. So we first acquire the raw data, and then create a derived data set out of that. Because some users have the privilege to use raw data for 90 days, right? And beyond 90 days, this is retented, but anonymized data will survive for 13 months. So it doesn't happen on the fly. It is post-processing. Once we acquire the data, then there's a MapReduce job that is launched, and anonymization happens. Yeah.
Thank you.
Sure, thank you.